Okay, so capacitors. I am going to talk about simple linear parallel plate capacitor, in which when you have a charge in the top plate, you develop a voltage across it, and the relationship that you have is that charge is directly proportional to voltage. Let's try to understand why is charge going to be directly proportional to voltage. Right? Of course, charge is proportional to the capacitance. The more the capacity of a capacitor, the bigger the size of the capacitor. For example, if you see an electrolytic capacitors, they scale like that. The bigger the size of the capacitor, the more likely that they can have more charge. That's fine. That sort of makes sense. But why is charge related to voltage? Let's think about that. Okay, so I have this parallel plate capacitor. And here I do some effort, I do some work, and I add a charge to the capacitor. Now there was no other charge here, so the work in adding the first charge was minimum, maybe even 0. Yeah. But when I come along and I bring the second charge, then there's already a charge sitting there, so that opposes the charge that I am bringing. So a little bit more of work is needed. Yeah. Then as I bring the third charge and fourth charge, so basically as I am loading up the capacitor, I am doing more and more work. Work, remember, work per unit charge is voltage. So if you look at this curve, it's a linear curve. Okay, and in this linear curve, of course, the slope Q divided by V or dQ divided by dV is what is called C. So dQ by dV is C. It's a direct. If I take a derivative of this and assume C is constant, usually you may not always be able to assume C is constant, but I am taking a nice linear simple parallel plate capacitor. So when I take a derivative, then when I take the derivative of charge divided by derivative of voltage, I get the capacitance. Okay, so let's talk about what is the energy if I have charged this capacitor to a voltage, let's say V1. Okay. So if I have charged this capacitor to a voltage V1, that means somewhere here is V1. Okay. And basically, since I know that charge times voltage is energy, in this curve, the area of the curve, right? If the charge was always the same, it would have been a rectangle. That would have been an area we know. But the area of this curve, Q versus V curve, because every time you add a certain charge, the voltage is increasing. As you keep adding charge, the voltage keeps increasing. Initially, no work is done to add the first charge, but eventually, a lot of work is done to add that charge. So, if I take my what I am calling energy, right? So energy, because this is it's not independent of V, right, is basically my integral, right, of Q with respect to V. Now in this case, Q we know is a linear relationship C V. So this gives you the half CV, okay, 0 to V1, 0 to V1, half CV1 square. So that's the energy of a capacitor. It's not the voltage of a capacitor, that's V. The energy of the capacitor is half CV square. Okay. So that's as far as the energy is concerned. Now the other part is of course dQ. So dQ, a small change in charge, is equal to a small change in voltage, proportional to a small change in voltage, right? Which also means that if I said it happened in a small duration of time, then your dQ by dt, which is current, that's your definition of current, rate of change of charge, is basically C times dV by dt. So this is the equation most people know, I is equal to C dV by dt. That's what it's coming from this fundamental idea that the charge is proportional to the voltage. The more charge I am putting, the higher the voltage of a capacitor is.